Hello, my name is Slama and I am an associate professor at CESI attached to LINEACT laboratory in France. And I am going to present our work entitled Dual Spatial Graph Convolution Network and Transformer Graph Encoder for 3D hand gesture recognition. And I will start by presenting a brief introduction to this work. So, hand gesture recognition consists of understanding the meaning of some motion of the hand, which changes the way we interact with our environment. And it has many applications in different areas: health, gaming, robotics, virtual reality, and many other areas. And based on the chosen modality, hand gesture recognition approaches can mainly be split into two categories: image-based approaches, which employ either RGB or RGBD images, and skeleton-based methods, which use sequences of 2D or 3D Euclidean coordinates of the hand joints. And as skeleton data provides efficient computation and storage, in this work we are interested in developing a robust system for skeleton-based hand gesture recognition. Now let me introduce our proposed model. In this paper, we proposed a graph-based approach. As input data, we consider the 3D hand skeleton sequence as a graph sequence, taking advantage of the natural graph structure of the hand. Then we extract the most important descriptors with two modules. First, in a spatial domain, a spatial graph convolution network is used to extract hand features at each frame. And then, in a temporal domain and respecting the graph structure of the spatial features, a transformer graph encoder is proposed to extract inter-frame relevant features. Finally, a global polling operation is used to aggregate the graph into a representation that can be interpreted by our classifier. Now let's go through each module of this architecture, and I will start with the input data. Here an example of a gesture. As we can see, the sequence consists of 3D hand skeleton in each frame, capturing the 3D coordinates of the hand skeleton. These coordinates are the result of a hand pose estimation coming from depth images. And in order to consider the 3D skeleton as a graph, we encode skeleton joint neighborhood considering the joint adjacency, which leads us to construct an adjacency matrix as shown in this table. For spatial feature extraction, we use Spatial Graph Convolution Network. This is done by aggregating the information of each node in the graph with the information of its direct neighborhood to form a new feature vector. The output will be a graph sequence containing the extracted spatial features of each node. And the next step is the temporal feature extraction using a Transformer Graph Encoder, which is a model that we introduced in this paper inspired by the original Transformer model. This module learns the inter-frame correlation locally between joints, and these local features are then used to learn the global motion of the hand. The Transformer encoder is composed of multiple identical encoder layers stacked together with each one feeding its output to the next. Each encoder layer applies two operations: multi-head attention and simple fully connected feed-forward network. Finally, the temporal features are processed by the classifier. This process is preceded by a global average pooling layer to transform the graph sequence into a collection of feature vectors which can be digested by the fully connected layer. Now let's go through experimental results. In this paper, we tested our approach on 3 popular benchmarks for hand gesture recognition captured in different contexts: augmented and virtual reality context, automotive, and daily life tasks. We follow the same experimental protocol as previous papers to produce our results. We need to mention that we use a data processing step to prepare the data, mainly translation and scale normalization to be invariant to rigid transformation, and noise augmentation and random moving, which help preventing overfitting and allows the model to generalize better. More information on data processing and the training details are detailed in our paper. So we evaluate our method by comparing it to other hand gesture recognition approaches that use the 3D skeleton modality. And the results are shown in this table, which prove that we achieve with our method competitive results. On Briario dataset in particular, where the gestures are performed by different subjects up to 40 ones, we achieved about 96% accuracy, outperforming other state-of-the-art methods. This demonstrates the intra-class robustness of our method and its capacity to recognize the action while ignoring subject-related features. So let's conclude and present our future works. To conclude, we can confirm that using end-to-end graph data structure augmented with attention module is efficient to model spatio-temporal relationship. Moreover, our proposed approach performs efficiently in different contexts and datasets. And in future works, we intend to evolve this architecture to online hand gesture recognition and to test it on collaborative robot controlling. Thank you for your attention.